Hello, dear learners! Welcome back to the Lesson BCE YouTube channel. Today we will see the solar system, formation, the sun, planets, and small bodies. Oh, and right off the bat, don't forget to subscribe and like our channel. We've got a fantastic explainer for you today, exploring the origins, the structure, and the immense scale of our local cosmic neighborhood.
Here is a super quick look at our agenda. We are tracing a journey from the very birth of the solar system, 4.6 billion years ago, all the way out to the math we use to measure the stars. 6 quick sections, so let's just dive right in.
Section 1. Solar System Formation. Let's start at the very beginning. I want you to pause and just think about this for a second. How exactly does a swirling, chaotic cloud of interstellar gas actually organize itself into the precise, orbiting planets we know today? It sounds impossible, right? Well, it's all explained by the nebular hypothesis. Picture this: about 4.6 billion years ago, a massive cloud of gas and dust, a solar nebula, collapses under its own intense gravity. As it collapses, it starts rotating faster and faster. Most of that material gets pulled right into the center to form a protosun. But what about the leftovers? That remaining material flattens out into this massive, rotating protoplanetary disk. Inside that disk, tiny particles literally just start bumping into each other and sticking together. It's a process called accretion. Over time, those tiny clumps grow into planetesimals, and eventually, boom, you get our planets.
All right, moving on to Section 2, Inside Our Sun.
Now that we've got our system formed, let's talk about the big boss at the center. The sun literally holds 99.8% of all the mass in our solar system. It's entirely gaseous, and it's powered by nuclear fusion happening deep inside its core. Basically, hydrogen nuclei are constantly smashing together to form helium, releasing a massive amount of energy. Remember Einstein's famous E=mc² equation? Yeah, that is exactly what's happening here. This intense heat travels outward through the radiation and convection zones and eventually passes through the atmospheric layers, the photosphere, the chromosphere, and finally the corona. And hey, all that intense energy? It can trigger solar activity, like sunspots and solar flares, which can actually mess with our satellites and communication systems right here on Earth.
Looking at this diagram, we can actually trace the exact evolutionary path our sun is going to take. Right now, it's a super stable main sequence star. But following this sequence, it will one day expand into a massive red giant, puff off its outer layers as a beautiful planetary nebula, shrink down into a super dense white dwarf, and then finally, way down the line, cool off into a dark black dwarf. Let's journey outward now. Section 3. The Terrestrial Inner Planets. So right near the sun, we hit the terrestrial planets. Because they formed so close to that intense solar heat, inside what planetary scientists call the frost line, only the tough stuff survived. Heavy silicate rocks and metals coalesced into these really compact, solid worlds. You've got Mercury, the closest planet with basically no atmosphere, then Venus, the absolute hottest planet thanks to its thick, heat-trapping carbon dioxide atmosphere. Next is Earth, our home, loaded with liquid water and, life. And finally Mars, the red planet, which actually shows a lot of evidence of ancient flowing water.
Next up, Section 4, the Jovian Outer Giants.
Once we cross that frost line, things completely change. Look at the sheer contrast here. The massive Jovian giants, Jupiter, Saturn, Uranus, and Neptune, totally traded solid rocky surfaces for massive, swirling gas atmospheres. Jupiter has its famous Great Red Spot Storm, Saturn has those iconic rings, Uranus literally rotates on its side, and Neptune is whipped by incredibly strong winds. Because they formed out in the freezing outer regions, they could grab onto massive amounts of lighter materials like hydrogen, helium, and ices, allowing them to grow absolutely huge.
Okay, Section 5, Asteroid Belt and Small Bodies.
So what actually separates those dense rocky worlds from the massive gas giants? It's the asteroid belt. This is basically a rocky debris field sitting 2 to 4 astronomical units from the sun. It's packed with millions of rocky bodies that Jupiter's massive gravity actually prevented from ever forming into a full planet. But that's not all the small stuff in our neighborhood. We've also got dwarf planets like Pluto hanging out in the distant Kuiper Belt, icy comets that grow those stunning, glowing tails when they get near the sun, and meteors, which are the beautiful streaks of light you see when a space rock hits our atmosphere.
Finally, Section 6, Measuring Cosmic Distances.
To truly grasp our place in the cosmos, we have to talk about the math astronomers used to measure these staggering distances. We use something called the astronomical unit, or AU. This is the exact average distance from the Earth to the Sun. Let me give you a quick solved example to put this in perspective.
Light takes about 8 minutes to travel from the Sun to Earth. Since the speed of light is roughly 3 times 10 to the 8th meters per second, you just multiply that speed by 480 seconds, and you get this massive distance of roughly 1.44 times 10 to the 11th meters. It's a huge baseline.
And we use that 1 AU baseline to peer even further out into the galaxy using a trick called stellar parallax. As Earth moves around the Sun, a really close star will actually look like it's shifting against the background of stars that are further away. By measuring that tiny shift, the parallax angle, and using some simple trigonometry, astronomers can literally calculate the exact distance to neighboring stars. For example, using this math, we know a star like Proxima Centauri is 1.29 parsecs away. Pretty brilliant, right?
Let's do a really quick key summary. Our solar system formed from a collapsing nebula. The Sun generates its immense energy through nuclear fusion. Mercury, Venus, Earth, and Mars are our terrestrial planets, while Jupiter, Saturn, Uranus, and Neptune are our giant planets, and they're separated by the asteroid belt. Don't forget Pluto is a dwarf planet. And finally, we use the astronomical unit and parallax to map out the stars.
So, now that we have completely mastered our own local neighborhood, what lies beyond the universe's largest structures? What is out there beyond the cosmic web? I want you to really ponder that for our next lesson. Thank you so much for watching. Don't forget to subscribe and like our channel for more physics and astronomy lessons. Keep exploring, everyone.